The last thing we'll talk about for linear regression, and I assure you that there's a lot of things we did not talk about here. This could be a full course all on its own. The last thing we'll talk about, coefficient of determination. How do we know if the regression is actually a good fit? We've talked about how to determine if the regression is significant, but we don't know if it's a good fit or not at this point, right? So if you have a number of observations, you can define for the line of regression a coefficient of determination. We call it R-squared, and it is going to be read right off of the ANOVA table, 1 minus sum of square errors divided by the total sum of square. And in a sense, it tells you what proportion of the variance, what proportion of the total sum of squares is explained by the regression. You can rewrite this as the following expression, and this is just a sum of squares regression. What proportion of the variation is explained by the regression that you have found? R squared will always lie between 0 and 1. When R squared is close to 1, we consider that the fit is very good. But be careful. As far as goodness of fit statistics go, R squared is not always the best choice. There's other factors, including the number of observations, which can actually affect the coefficient of determination. You often end up having to use some other methods, some other ways, such as, well, if it's true that we have a linear relationship between x and y, how well can we predict new values of y by just looking at the x? If you make good predictions, then you have a good model. But the number of observations can affect the coefficient of determination, and there's other things that can come into play. You may have to think of other ways to determine the goodness of fit of your regression. For the fuels data set, you can read the R-squared statistic directly from the output in R or from the ANOVA table that you have built. We know what SSE was, we know what SST was. In this case, we get an R-squared of about 87.74 or 88%. So 88% of the variability in the response Y can be explained by the line of best fit. But it's easy to mistake that explanation for a causal relationship. It's not a causal relationship. So if you're faced with a regression problem, what should you do? In the case of simple linear regression, you have only two variables, a predictor and an output. So start by drawing a scatter plot. Visually, does it make sense that the assumptions of linear regression are met, that the variance is constant in the noise, that there is a linear relationship? Then you will find the regression line using the formulas or the code in R. You'll check the appropriateness of a linear fit, perhaps by computing the correlation coefficient or the significance of the regression. You'll check goodness of fit or confidence intervals for the regression line. Check your model assumptions by looking at the residuals. Like one of the things we've said is that the residuals should follow a normal distribution. So if you just look at the residuals, do they follow a normal distribution? Then you'll make predictions if it is appropriate for you to do so. In the slides, I have provided you with two other fully worked out examples. I strongly urge you to take a look at the explanations. I will not go over these explanations in person. And as I mentioned a number of times, there will be a video showing you how to do this in